Hey folks, I've got a couple of Newton's second law examples for you. This will probably cover the next couple of videos. There's an infinite number of examples we could give you, so I've selected a few and we'll do them out. Now, by the way, on a lot of the examples, I won't have any numbers in there. I'll just have variables, and we're going to find answers in variable form. Plugging in numbers is usually the easy part. I always suggest to my students that you wait and plug numbers in. You wait until you have to plug numbers in. Oftentimes, you will find patterns in the equation answers you get that you wouldn't necessarily recognize with using numbers right away. So from here on out, you'll probably notice that for the rest of the semester, a lot of the problems I'll do, I'll never pull a calculator out. There won't be numbers. So keep that in mind as we go. All right, so the first example I've got drawn, I'm going to start really simple. Let's say we got a cart, mass M, and we're pushing on it with a force F. Oop, and I forgot. We're pushing at an angle theta to the horizontal. And we're going to assume no friction here. That's later. And I want to have you guys determine two things. Let's determine the normal force and the acceleration of the cart in terms of the givens and fundamental constants. This may be the first time I've mentioned that. I don't know for sure, but basically we're going to get an answer that's not a number but an equation. And the equation can only have the givens and fundamental constants. So the givens were F, M, and the angle theta. And in this problem, the fundamental constant that may come into play is the magnitude of the acceleration of gravity, g, which we know is 9.8, but we're going to leave it as g. So we're not going to plug any numbers in here if we can. All right, so the first step on these kind of problems is you're going to draw an FBD. What I have drawn here is just a sketch. It's not an FBD. We're going to take that object, the cart, and free it from its surroundings and draw the forces acting on it. So I'll do that below, okay? And I'm actually going to draw two FBDs. So the first FBD would be if you were doing an AP exam, let's say, and College Board said to you, hey man, draw an FBD, all right? Then this is what I'm going to draw. So literally just draw the forces as they lie and not break anything down. So I have the force I'm pushing with, and the way you do this on an FBD is you draw the arrow starting on the dot and then away from the dot with the correct direction. So there's that force, okay? Now, you're on Earth, so obviously gravity is going to be acting, so that's the force of gravity, okay? And then is there anything else touching the cart? Well, the ground is going to hold it up, so that's your normal force. Now, I did not draw these to scale. In this case, the normal force is going to be bigger than the force of gravity. Oh, and that's another thing. The force normal is not always equal to the force of gravity, and in this problem it won't be. So kind of keep that in mind. All right, so that's the first FBD. It would be I'll call that the College Board FBD, that's just the forces as they lie. We're going to draw a second FBD. I'll use red. And what I'm going to do is I'm going to break the forces down into components. And the simple way to do this is to look at two directions. The first direction is parallel to the motion of the cart. The other direction is perpendicular to the motion of the cart. This pretty much will work every time. You're going to break every force down into either parallel to the motion of the cart or perpendicular. Now, the good news here is two of the forces are already in one of those directions. The force of gravity is perpendicular to the cart, so I can just redraw that. The force normal is perpendicular to the cart, so I can just draw that, okay? Oh, and I'll make these red for you. All right, so those two are all set. The force that I'm pushing with, that is neither perpendicular nor parallel to the cart. So it does have two components. It has a force a component that's parallel to the cart. Now, by the way, how would you calculate that? Well, the parallel component in this case is the adjacent leg of that triangle, so it's cosine. So it would be F cosine of the angle. And that force also pushes down, so I'll draw a second down arrow here, and that is force perpendicular to the motion, which is force sine of the angle, okay? So this, by the way, is probably the hardest part of the problem. And once you're done with the FBD, the rest of it's usually really easy. Okay. Now, to figure out, I'll actually start with the acceleration of the cart first. So I'm going to look at net force in the parallel direction has to equal ma in the parallel direction. How many forces do we have in the direction parallel to the motion? Well, we only got one. That's F cosine theta. So you got F cosine theta equals ma. And if you solve for a, you get F cosine theta over m. Okay. So very simple equation. If I gave you a numerical value for F, for theta, and m, you can plug them in. You get a numerical answer for a. Okay. So that would be the acceleration of the cart in terms of the given fundamental constants. Now, how about the normal force? Well, then we got to look at the perpendicular direction. Net force perpendicular equals ma perpendicular. So what's the perpendicular acceleration? Well, there'll be a few people who say, oh, I got it. It's 9.8. It's G. It's 9.8. No. This cart, when it moves, it's moving only to the right. It's not accelerating up or down at all. So A perpendicular equals 0. Okay. And this is one of the reasons we split our forces up into parallel and perpendicular to the motion, is because one of the accelerations will usually be 0. So let's go with up being positive. I'll draw a positive arrow on my FBD. So if I do that, I've got F normal minus, there's two downward forces. You got FG acting downward, and you've got F sine theta acting downward, and that all equals 0 because there's no vertical acceleration. Now there's two quick steps here to get Fn by itself. First of all, Fg was not one of the givens, right? We were only allowed to use force, mass, theta, and little g. So the force of gravity is equal to mg. So there's that. And then minus F sine theta equals 0. And then if you get Fn by itself, you get the answer. You get mg plus F sine of theta. So that is the magnitude of the normal force. And again, if I gave you a mass and a force and an angle, you can plug them in. You'd get a numerical answer for Fn. Now, by the way, how would these answers change if this force, okay, instead of pointing up or pointing down, we're pointing up at the same angle? Let's assume it's the same angle, okay? Well, the only thing that would change would be the direction of this vertical arrow there. F perpendicular would be up. It would be F sine theta up, okay? That would not affect your acceleration at all. Nothing there would change, okay? If there's no friction, that acceleration will be the same. What would change down here in finding F normal is now F sine theta would point up, so you'd put a little plus there, and there'd be a plus there, and then there'd be a minus there, and that's your answer. And by the way, that's another reason why you want to keep things in variable form as long as you can, because it's really easy to change stuff and to fix stuff if you need to. A lot easier than plugging numbers in, okay? Now, I'll do one more example on this video. Let's say that you have that cart on an incline. So you're on an incline. Here's your cart. Okay, it's got a mass m. The incline is at an angle theta, the horizontal. And for now, let's just leave, that's just all we have. And we have no friction. And same thing, I want to find the acceleration of the cart and the normal force acting on the cart. Okay, so again, we're going to draw an FBD. Okay, so I'll do that down here. Okay, what forces act on the cart? Well, first of all, we're on Earth, so gravity acts straight toward the center of the Earth, which is straight down the picture. And then what else is touching the cart? Well, the ground is going to push away perpendicular from the ramp. So that would be approximately this way. Okay, and that would be your College Board FBD. Now, how would we break this down to actually solve a problem? And I'll do this in red. Okay, so again, we're going to look at parallel to and perpendicular to the motion. So parallel to the motion would be along the ramp, and perpendicular would be perpendicular to the ramp. Okay, well, Fn is already perpendicular to the ramp, so I don't have to do anything with that. The force of gravity, however, is not. Okay, now a little geometry here. This angle here is also theta. Now, if you sit and draw triangles and such and think about it, you'll eventually figure out that these two angles, this one and this one, are congruent. Okay, so the force of gravity has two components. the force of gravity points straight down. Part of that is perpendicular to the incline, and part of that is parallel to the incline. Okay, so there's a little right triangle. So here is force of gravity perpendicular. And I'll label that force of gravity perpendicular. Now, how would we calculate that? Well, that's the adjacent leg to this triangle, so we're going to use cosine. So this would be force of gravity cosine of theta, which would equal mg cosine of theta. And then the component of that triangle that's opposite that angle is sine. So the component of gravity that's actually making the cart accelerate down the incline would be, I'll call it Fg parallel, which is equal to Fg sine of theta, which is equal to mg sine of theta. Now for this problem, I will say down the incline is positive, and then perpendicularly away from the incline is positive, okay? So that's my coordinate system. I'm calling down the incline positive because the acceleration will be down the incline. Now, by the way, it doesn't mean the cart's moving down the incline. It could be coasting up the incline, but slowing down. But in either case, it's accelerating down the incline. So if I look at the acceleration first, I'm going to do net force parallel to the motion equals ma parallel. And the only force I have parallel to the motion is my mg sine theta, and that equals ma. Notice the mass cancels out here, and so you get a equals g sine theta. So that is the acceleration of the cart down the incline. Now, what about the normal force? Okay, well, we got net force in the perpendicular direction equals ma perpendicular, which we know is 0. This cart is not accelerating away from the incline, nor is it crashing through the incline. So a perpendicular is 0. So we have Fn is pointing away from the incline, and then we have mg cosine theta is pointing into the incline, and those have to equal 0, and you got Fn. Fn equals mg cosine theta, okay? Now, one last thing I'll add to this problem. What if we added a force? So what if you started pushing up on the cart, okay? So let's say you push this way. I'll just call it F, okay? How would that change our problems? Okay, well, for finding the acceleration, assuming you still call down positive, then you'd have a negative F out front here. Now, in this case, you could not cancel the m's out because you'd have to have an m in all three terms, and we don't have that. So then the masses would not cancel out, and you would have A would equal negative F plus mg sine theta all divided by m, okay? How would this affect, so your acceleration would not be different. How would this affect your normal force? Well, it wouldn't, because the way I've drawn this force here, the way you're pushing on that cart, none of that force is parallel or none of that force is perpendicular to the incline. So that would not affect your normal force at all. Now, in a later video, I do a problem where that force you're pushing with is not parallel to the incline, in which case normal force is affected, and we kind of go through that. Hope that video was helpful, and the next video will have more examples for Newton's second law. Have a good one.